Hi, everyone. Thank you for joining for today's webinar. My name is Sakshi Sethi, and I manage OIDA membership here at OSA. I'm really excited to introduce today's presentation. It's by Optotest and US Connect. But before we get started, I just want to take just a minute to review a couple of housekeeping items. So if you need any assistance during today's presentation, just send us a chat using the icon at the bottom of your screen. If you just hover your mouse over this webinar, you'll be able to see your panel pop up. So you can send me a message directly there. I'd be happy to assist with any technical issues or if you have any questions. We also really encourage you to ask our speakers questions during the presentation. So at the bottom of your screen, you'll also see a Q&A icon. You'll just simply type your question and submit. If you want to submit it anonymously, you have that option as well. And our speakers have decided to take and answer all of your questions at the end of their presentation. So we've allocated some time to engage in some Q&A. And finally, this webinar is being recorded, so OIDA will post the final video on our website so it can be available to everyone afterwards. So in case you have to drop off a little bit early or you want to rewatch this presentation later, I'm going to drop a link in the chat box shortly on where you can find the recording online next week. So that's everything I have for housekeeping. Thank you guys so much again for joining us. I'm going to go ahead and turn it over to our speakers, Chris and Shelly, and they're going to get us started.
All right, so let me share my screen here. Can everybody see it?
Yes.
All right. Hello, and thank you for attending our webinar on testing MTP and MPO assemblies. I'm Chris Heisler, the CTO of Optotest Corporation. I've been in the fiber optic test and measurement field for close to 15 years. I've helped conceptualize and develop test equipment that improves the testing throughput of fiber optic patch cord production lines while maintaining high levels of accuracy. US Connect is partnering with Optotest for this webinar. Shelly Buchter will be presenting for US Connect.
Thank you, Chris. Hello, everyone. My name is Shelly Buchter. I've been working in fiber optic connector industry for 25 years. The last 5, I've been a product line manager at US Connect, where I have responsibility for the MTP connector components and adapters, which includes the Mtpmpo connector. In addition to these product responsibilities, I also participate in TIA standard committee meetings focused around MPO multi-fiber standards. At this time, Chris is going to provide a short overview of Optotest.
Thank you. So a quick overview of Optotest. We've been designing fiber optic test equipment for close to 20 years. We tailor test equipment to the needs of our customers. Roughly 60% of all of our insertion loss, return loss test equipment is used to qualify MPO cable assemblies. We take pride in simplifying the test and measurement process for our customers to help increase efficiency. We're dedicated to producing reliable, responsive, and accurate test equipment. Our products are designed and manufactured in the USA, and we are an ISO 9001-2015 compliant company.
US Connect was established 28 years ago to expand the use of MT ferrules and MTP brand connectors through design, manufacturing, and high precision components. Since 1992, our multi-fiber ferrule offering has expanded to include clear prism light turn and prism MT lens ferrules, prism light turn connectors, and MXC connectors and adapters. More recently, we released our Element single fiber connector brand, which includes our newest connector, the MDC connector. With a strong foundation and high density connectivity, we also evolved into offering optical packaging like silica and polymer lens solutions. In addition to these products, we offer several brands of cleaning tools for many types of fiber optic connectors. Overall, US Connect is more than just a connector manufacturer. We have a complete ecosystem to support our customers through a library of application notes and a thorough face-to-face training on how to terminate connectors per the best practices. Jumping right into today's topics, I'm going to start the webinar with a brief introduction to MPO basics, dive a little bit deeper into key components that contribute to optical performance, and end with an introduction to the Mtpmpo configurable connector and highlight where it could be used in fiber optic testing. The basic MPO mated pair includes a female plug with guide pin holes, a male plug with guide pins, and an opposing or aligned adapter that mates these two plugs. Two MPO connectors should be intermatable as long as they are dimensionally meeting the IEC 61754-7 standard or the TIA 604-5 interface standard. IEC separates one row variant into 61754-7-1 and two rows into 7-2, where TIA includes all versions into Focus 5, one document. Another standard that can be referenced is TIA 568.3-D. This standard includes details on polarity types and specifically designates opposing key adapters as type A and aligned key adapters as type B. Your system's connectivity methods will determine the appropriate connector and adapter for maintaining polarity. Diving deeper into this basic system, fiber alignment, fiber tip contact, and fiber tip geometry are what contributes to the quality of optical performance. Axial, angular, and angular fiber alignments determined by the quality of an MT ferrule and the guide pins, not the adapter. It's the true position of the fiber holes in the MT ferrule relative to the guide pin holes that is crucial. It's also the tolerance held on the fiber holes and the guide pin holes, along with the diameter tolerance on the guide pins themselves. All of these components and their dimensional limits contribute to the quality of fiber alignment and ultimately contribute to optical performance. Fiber tip contact, which is determined by end face geometry and connector spring force, is another contributor. IEC 61755-3-31 is a great reference and provides guidance on single mode APC parameters and specifications to assure physical contact. These parameters are generally accepted as guidelines for multi-mode applications. The last contributor listed is fiber tip cleanliness and quality. Debris can result in link failure by blocking the light when a particle migrates to the core, or in loss of physical contact due to that particle on the end face. IEC 61300-3-35 contains the visual acceptance criteria that for allowable multi-mode and single mode polished fibers. Adhering to this specification should result in acceptable optical performance. Next, I'll hand the lead over to Chris to highlight the different optical performance test systems.
Chris, I think you're on mute.
I am. All right. So in this presentation, we'll be discussing fiber optic measurement principles, equipment selection for MPO assembly testing, reference cord setup, measurement processes for specific DUT types, comparison of measurement methods, unidirectional versus one-sided, common pitfalls and solutions to those. There are two main methods to measure return loss on cabling assemblies. These are the CW method and an OTDR pulse-based method. The CW method is inexpensive, however, it is difficult to implement for MPO assemblies. The CW method requires a user to take an additional step of reducing stray reflections. This typically means that the insertion loss and return loss need to be measured separately. Methods to reduce stray reflections are cumbersome and can lead to erratic measurements. Manual wrapping a ribbon cord or mating an MPO connector to a matching block are not good practices. The pulse-based method of measuring return loss enables the ability to measure insertion loss and return loss with the same setup. No need for terminating the back connector to isolate the measurement to the front connector. In the diagram, the front connector can be measured independently of the back connector. MPO assemblies are multi-fiber assemblies, and as such, a multi-channel switch-based system should be used. A simplex setup is just too cumbersome and leads to inaccurate results. MPO assemblies require a lot of data gathering for the reference process and measurement process. It is best to automate the testing process with a software package that can manage this data. The software guides the instrument through the measurement process efficiently and stores reference and measurement data. When investing in MPO test equipment, it is best to understand current and future needs of your cable production. Does your system require expanding in the future? If so, moving up in channel count is typically more expensive when doing it in increments, and sometimes when moving from a 12 fiber based MPO connector to a 16 fiber based connector, a new optical power meter is needed. When selecting a system for testing MPO assemblies, one needs to pay careful attention to the optical power meter. The optical power meter is crucial for accurate measurements. Poor selection of a power meter may reduce accuracy of the measurement, as well as limit system expandability if it can't accommodate larger channel counts. MPOs have a wide spacing between the two outermost fibers. For 12 and 24 fibers, this distance is 2.75 millimeters. In the graphic below, one can see a detector that doesn't provide full coverage, and light from the outer fibers is not completely captured. Increasing the size of the detector provides full coverage. For 16 and 32 fiber ferrules, this distance is 3.75 millimeters. One must select an OPM that has full coverage to capture all light from the outermost fibers. A detector system that works for 12 and 24 fiber applications may not work for 16 and 32 fiber applications. So as you see, the detector for the 16 fiber ferrule does not completely cover the light. You'd have to get a larger detector. Given the wide pitch of fibers in MPO assemblies, typically an integrating sphere with a large aperture or a large area detector, 5 millimeter or 10 millimeter, is necessary. For standard telecom wavelengths, 1310 and 1550 and etc., InGaAs is typical. However, for applications for 850 nanometers only, which applies to OM2 fiber and up, an inexpensive silicon detector can be used. There are two housings that a detector can come in. They come as either a remote head or a panel mount detector. A panel mount detector is mounted on the front panel of the instrument. This requires the user to connect the back of the DUT or receive cable to the panel of the instrument. With rigid cables, this can be very cumbersome. A remote head detector has the detector in a small, semi-portable housing. The detector is tethered to the instrument with a flexible cable. This allows for a wide range of movement. For stiff, rugged assemblies, the technician can simply move the remote head to the DUT rather than needing to bring the DUT to the power meter. Now, there are three options to achieve a multi-channel insertion loss and return loss test setup. The first is a simplex IL-RL set with an external optical switch. These systems are great for expandability. Switches can be added to increase channel count. Adding a 1x2 and a 1x24 switch can take a 24-channel system and make it a 48-channel system. These additional instruments and cables, however, may lead to a crowded workspace with cables taking up much of the space. Also, during calibration, the optical switch is not accounted for, so this may lead to inaccuracies during the testing. Method 2 is an instrument with an internal switch. An all-in-one system is great for a small footprint on the workstation and leads to a simplified setup. Since the switch is integrated into the system, the switch insertion loss is accounted for during the calibration of the equipment. Expandability is difficult, and the setup becomes complicated if one wants to add external switches. The third system is a compact, dedicated MPO test system. A dedicated MPO test system is great if the system will be dedicated to MPO assembly testing only. The OP940 CSW has a compact footprint and cable management is minimal since it doesn't require a fan out due to it having an MTP connection at the front panel. Expandability is difficult as the switch can't be cascaded. Since this has an MTP connector on the front panel, testing simplex cords would be difficult, and as such, fan outs would be complicated to test as well. When setting up an MPO cable production station, careful attention to the reference cord setup should be taken. An equipment cord connects directly to the instrument and is intended to not be replaced often. It is typically a fan-out cord that combines simplex connectors into a single MPO connector. These cables are relatively expensive and as such should be treated with care. A launch cord interfaces directly with the DUT. It is connected to the MPO connector of the equipment cord via a mating adapter. The open connector of this launch cord will be mated to the DUT. This open connector is considered the reference connector and as such should be maintained and cleaned routinely. Note, for typical MPO assembly test setups, it is recommended to keep all equipment and launch cords as type A cords, as well as all mating adapters should be type A, which are key up to key down. This is a standard black adapter. This maintains a one-to-one mapping, which keeps maintaining results simple. Intermediate connections, such as the connection between the equipment cord and launch cord, need to have low insertion loss and high return loss. This maintains a high level of accuracy on the DUT measurements. When connecting the launch cord to the equipment cord, the insertion loss and return loss should be verified. When using a system to test both single and dual row setups, 2 equipment cords based on the single row count should be used. In this case, 2 12-fiber fan-out to MPO cables connected to the instrument. For single row assembly testing, attach a single row launch cord to the equipment cord. For dual row assembly testing, so like a 24-fiber test, use a fan-out that has 2 single row connectors combined into 1 dual row connector. In this image, it is the 2 12-fiber MPO connectors to 1 24-fiber MPO connector. When setting up the testing space, use reference cords that match your requirements. There are space constraints as well as handling requirements. Your reference cord needs to be able to withstand normal handling practices in your manufacturing environment. A jacketed cord is rugged and durable, but does not allow for easy gender changing. A bare ribbon cord allows for easy gender swapping, but it is fragile and the binding material can break, causing the cable to fray. An Mtpmpo cord is the best of both worlds. It allows for gender swapping and is rugged and able to withstand rough handling. I will now pass the presentation back to Shelley to discuss the Mtpmpo connector system.
Thank you. Managing multi-fiber launch leads and whether they should include pins or should not include pins, or whether they should be key up or key down, can be simplified with the Mtpmpo configurable connector. The Mtpmpo connector includes all of the MT features such as elliptical guide pins and floating ferrule, plus it's designed to reduce debris generation. It has a consolidated push-pull sleeve similar to the SC, and it is reconfigurable. From concept, the Mtpmpo components were developed to reduce debris generation. Specifically, the materials chosen for the housing assembly and adapter were picked to reduce insertion and retraction forces while minimizing the latch and housing wear. As stated earlier, less debris means there's less chance of loss of physical contact. Also, the ferrule true position in the housing of the Mtpmpo was tightened for optical course alignment between the guide pins and the guide pin holes. Better alignment produces less optical loss. Because the pins and polarity can be changed without removing the housing, the reconfigurable Mtpmpo connector is an ideal choice for launch leads and when validating polarity. Using the field tool and pin exchangers means that there is no handling, no dropping, or losing of individual pins. An aqua exchanger captures the multi-mode elite or single mode grade pins, and the yellow exchanger the single mode elite grade pins, allowing the installer or technician to manage and store pins in a cartridge for reuse in the future. A suggested procedure would be to set up and test all of the jumpers of one configuration, and then reconfigure the Mtpmpo connector and test the remaining jumpers of the other configuration. At this time, Chris will continue the presentation on reference leads.
Thank you, Shelley. Multi-mode reference cords throughout should be constructed of non-bend insensitive fiber. Non-bend insensitive fiber allows for launch conditions to be better maintained as the light passes through intermediate connections. This is ideal for encircled flux compliance. If the instrumentation is encircled flux compliant, using non-bend insensitive fiber will better maintain this launch as it travels down the link. Optotest can supply reference cords built from non-bend insensitive multi-mode reference grade 50 micron fiber and we have the stance that these cables are a must when testing with an encircled flux compliant launch. Encircled flux must be maintained through connections, and as such, high quality connectors should be used on the equipment cords and launch cord matings. Non-bend insensitive fibers should be used to help maintain an encircled flux compliant launch. So for all IL-RL measurements, the systems must be referenced. What does an insertion loss reference consist of? It consists of taking a baseline optical power measurement for each channel and each source wavelength. For a 12 fiber dual wavelength test, there will be 24 optical power measurements stored for the reference. These will be used to calculate insertion loss later. Now, continuing to look at the referencing process, a return loss reference typically requires the pulse-based system to find the location where the return loss will be measured. This is usually at the position of the reference connector. A pulse is sent out to find the open end of the connector. The reflection comes back, and based on the time it took to return and the magnitude of the returned pulse, the location and the reflection size are known. In this case, the reflection is at 3.0 meters, and because this is a flat connector, the reflection is about 14.7 dB. For single mode MPO connectors, the connector is angled, and as such have a small undefined reflection value. Angled open connectors can have a range of values from the mid-50s to high 70 dB. The value depends on the polishing process, but either way, this reflection is not defined well. One could use a short APC to open PC reflector stub to introduce a defined reflection during the referencing process. This stub would only be used for return loss referencing and on angled assemblies, and would be removed for IL referencing and when measuring DUTs. If during the referencing process a known reflection is used, one can use it to subtract out errors caused by lossy setups. Components that cause loss in the setup may lead to inaccurate return loss measurements when DUTs are measured. Some general rules for referencing. For IL referencing, always re-reference when the cabling setup changes. So if you're going to change out your launch cord, or if you need to adjust your equipment cord, one should go back and re-reference insertion loss. Develop a schedule for referencing. Sources will drift with temperature and time, so this may affect the insertion loss reference. It's common to re-reference a setup once every hour or two, even when the setup is not changed. The same rules will apply for RL referencing. When the length of the reference setup changes, one should re-reference return loss. So if you have a 5 meter reference cord and you exchange it out for a 5.5 meter reference cord, you'd want to re-reference return loss so that the system can find the new position to measure at. If nothing changes with the cabling setup, it isn't necessary to re-reference return loss at the same frequency as an insertion loss reference. Now for the more mandatory portion of any fiber optic presentation, cleaning and inspection. There should be clear guidance for cleaning and inspection for technicians working on an MPO assembly line. Due to MPO assemblies possibly having male pins, it is necessary to use dedicated Mtpmpo cleaning tools. These help to protect the various features of the MPO end face. When there is difficult to remove debris, using a little alcohol can loosen the debris so that it can be wiped away. The guide pins and guide pin holes are essential to a properly mated MPO connection. These should be routinely cleaned on the reference connector. This can be done with compressed air or a dental brush. The dental brush below has a thin probe that can slide into the guide pin holes and clean out the debris that may be clogged in the guide pin hole. Each DUT shouldn't only be cleaned every time, they should also be inspected. Cleaning an end face does not guarantee that all the contaminants were removed. To reduce damage to the reference connector, it should always be inspected. This connector influences the measurements on all connectors mated to it, and as such should be cleaned and contaminant-free. When a connector has contaminants, it is fair to assume that the connector it was mated to will also have contamination. When a dirty connector mates to another connector, typically the contaminants will transfer between connectors. Since cleaning and inspection is a pain point for many technicians, make this process simple and smooth. Use tools that can inspect all fibers at once. Some inspection scopes require the user to iterate through each fiber on the MPO connector. This is time-consuming and painful. The Manta W Plus system can see all fibers at once, up to 96. It has a wide field of view, allowing the user to see all 16 fibers of a single row 16 fiber ferrule, or all 32 fibers of a dual row 16 fiber based ferrule. When dealing with MPO assemblies, one must be cognizant of different polarity types. Polarity describes how fibers are routed from one side of the DUT to the opposite side. For MPO assemblies, there are three main types. Type A is a straight through component. One side is key up and the other side is key down. Position 1 of one side goes to position 1 of the other side. Position 2 to position 2, and so on. Type B is a component that creates a transposition of positions. This is a key up to key up assembly. Position 1 of one side goes to position 12 of the other side. Position 2 to position 11, and so on. Type C is a type A component with pairwise flips. One side is key up and the other side is key down. Position 1 of one side goes to position 2 of the other, and position 2 to 1, and so on. Shelley will now discuss the unique polarity changing capabilities of the Mtpmpo connector. Shelley, you're on mute.
I figured I'd forget about that. Thank you. For MPO connectors, changing polarity means that your housing must be removed, flipped over, and reinstalled. With the Mtpmpo configurable connector, then there is no need to remove the housing. It is eliminated. Polarity change is a quick and efficient one-step process. Two keys, one black and one white, are permanently mounted within the housing assembly. Via a one-step insertion into the field tool, the key swap so that the extracted black key on the top of the housing is retracted and the white key on the bottom of the housing is extracted. With this simple one-step process, it is very easy to check polarity and change polarity to move fiber positions 1 through 12 to 12 through 1. And now Chris will continue the polarity verification.
Thank you, Shelley. Prior to testing an MPO assembly for insertion loss and return loss, it is advisable to verify polarity first. You don't want to go through the process of measuring insertion loss, return loss on an assembly just to find out afterwards that the polarity has failed. You'd have to go back and remeasure insertion loss and return loss. A standard large area detector or an integrating sphere cannot differentiate polarity. This process should be a quick scan of an assembly. The OP415 on the right can scan 24 fibers within 1 second. Most common polarity types are type A, which is key up and key down, and type B, which is key up, key up. The TIA TSB 5069 was recently released in March, giving guidance on polarity and various components that contribute to polarity. Now for some basic measurement processes for MPO to MPO assemblies. This is a standard one-sided method, TIA 455-171B, method D, or method C2 of IEC 61300-3-4. So the most basic method is you take your launch cord, connect it to the optical power meter, and you're going to reference the power and find the position for that launch cord. Now, to measure the DUT, you're going to connect side A of the DUT to the launch cord and side B to the optical power meter. This measures insertion loss and return loss on side A, right? So now we need to measure side B. To measure side B, we're going to flip the cable, connect B to the launch cord and A to the optical power meter, and this will give us IL and RL on side B. Now, gender on MPO cables can be difficult to manage. Mating connectors of the same gender can damage connectors. This is a male-to-male mating, or result in poor alignment, female-to-female mating. So now dealing with gender, when testing assemblies with like gender, this would be male, male, or female, female, a single gendered launch cord can be used. So you have a male, male DUT or a female, female DUT. Now, for example, if we're testing a male, male MPO assembly, we would have a female launch cord. So we would connect our female launch cord to the optical power meter. We reference the power and find the position for the return loss. And then to measure, we're going to measure side A first, connect side A to the launch cord and side B to the OPM. And then you're going to get IL for A and RL for A. To measure side B, you connect, flip the DUT, connect B to your launch cord, and you're going to get IL for B and RL for B. You're going to get 4 measurements: IL, RL for side A, and IL, RL for side B. Now, when an assembly has unlike genders, so male, female, there are a couple options. If twice the channels are available, have 2 breakouts set up, one with male and the second with female. So if you're testing a 12 fiber assembly and you have a 24 channel system, you can have 2 launch cords set up that are 12 fiber, one that would be male and then one that would be female. So the referencing process occurs in 2 steps. First, launch cord 1 will be connected to the OPM and the reference is performed. So in this case, we're referencing our male launch cord, and then next we're going to reference our female launch cord. Now, to perform the measurement, to measure insertion loss and return loss on each connector, the proper gender connector of the DUT needs to mate to the corresponding launch cord. So now we have a female, male cable. We want to test all of our female sides with the male connector on the launch cord. So we're going to connect, in this case, side A is a female connector on our DUT. We're going to connect side A to our male reference launch cord, and side B will be connected into the power meter. This will give us insertion loss and return loss of side A. To measure side B, we need to use the launch cord that has a female connector on it. So side B is male. We're going to connect it to our female launch cord and then connect side A into the optical power meter. This will give us insertion loss and return loss for side B. So when an assembly has unlike genders, but the instrument setup doesn't have the convenience of having multiple launch cords, there are a few options. So for example, if you're testing 12 fiber assemblies, but you only have a 12 channel system, you don't have the luxury of having 2 launch cords. So one option is to test all sides of the DUTs that have the same gender, then exchange the launch cord or swap out the gender of the launch cord connector and test the other side of the DUTs. So for example, to reference, we have a male launch cord connector here. We're going to connect the launch cord to the OPM. We're going to reference insertion loss and return loss. And then since our DUT is female-male, we're going to test all female sides of our DUTs. So we're going to connect up the female side to our male launch cord and then the male side of our DUT into the optical power meter. We're going to measure insertion loss and return loss on the female side of this DUT. Then we're going to measure insertion loss, return loss on the female side of the DUT for the DUT2. Then we're going to go through all of our DUTs and measure insertion loss and return loss on all of the female connectors. So once all of the sides with one gender have been tested, the launch cord can either be swapped out with a properly gendered cord or the pins can be added or removed. Note, if the launch cord is physically swapped out, you should re-reference insertion loss. All right, so in this case, we have a male launch cord, and so we need to exchange it for a female launch cord. So now we have a female launch cord, and that could either have been done with a completely physically removing the launch cord and adding a new one that has a female connector on it, or if you have the luxury of gender swappable connector, you can just remove the pins. And if you just remove the pins, there's no need to re-reference insertion loss. So to measure, we're going to connect the DUT with the appropriate gender to the launch cord and the opposite side to the OPM. So we've already measured the female side of all of our DUTs, right? We need to go back and re-measure the male sides of our DUTs. So we're going to measure insertion loss and return loss on the male side of DUT1 by connecting it up to our female launch cord. Then we're going to measure the male connector of DUT2, and we'll go through and we'll measure all of the male connectors on our DUTs. So in the end, what we're going to have is all of our DUTs, all female sides will be tested for insertion loss and return loss, and all male sides will be tested for insertion loss and return loss. The previous routines show one standard way for testing fiber optic patch cords. Another method is typically referred to as the unidirectional method. This is referred to as unidirectional because the insertion loss and return loss are measured from one side. There is no flipping the DUT. This performs an IL measurement across the entire assembly, and it gives return loss measurements for each connector. So if we have our DUT here, we're going to measure insertion loss all the way through the entire DUT. This will give us an IL total. And then to measure return loss, we're going to send out a pulse. When it passes the first connector, we're going to get return loss of side A. And then as that pulse passes through, we're going to get return loss of side B. So the cable setup and process. The cable setup for the unidirectional method is fairly simple. The referencing process is similar to a standard one-sided test method. The power is referenced across all fibers, and the position of the launch cord's reference connector is found. However, this only gives the position of the front connector of the DUT. In this method, we also want to measure return loss on the second connector, so this position needs to be known as well. The measurement is performed by connecting the DUT to the launch cord and then connecting a receive cord on the back end of the DUT. The receive cord is then connected to the OPM. The insertion loss is measured through the entire link. The return loss is measured on the front side of the DUT. And to measure the return loss on the back side of the DUT length either needs to be known or the return loss instrument needs to perform a scan to find the back end of the DUT. So you're going to be able to measure return loss on the front end of the DUT, which is where the launch cord and the DUT are mated. You also want to measure return loss where the DUT and the receive cord are mated. And if you know the length of the DUT, the system will be able to find the return loss at that position. In this method, the DUT has two connections, one to the launch cord and one to the receive cord. Both of these connections have insertion loss, so the measurement will include both connectors in it. The pros of this setup is it gives all measurements in a single shot without needing to flip the cable. The cons, the IL measurements of each connector aren't independent of each other. If an assembly fails for insertion loss, it isn't directly known which connector is failing. You would need to do further single-sided testing for troubleshooting. So in comparing these results between the two methods, you have your DUT on the right. The standard method yields 4 results per fiber optic link. It measures the IL of A, the IL of B, RL of A, and RL of B. So you get 4 independent results. The unidirectional yields 3 results per link. So you get the IL total, which is the summation of ILA and ILB, but you don't know what the value of ILA or ILB is. You just get the total of it. You'll get RLA, which is the return loss of the front side, and you'll get RLB, which is the return loss of the back side. Now moving on to testing fanouts. Fanout cables represent a difficult test process similar to testing hybrid simplex cables, but 12 or 24 times more complicated. These testing processes usually require a lot of cable movement and possibly exchanging optical power meter adapters depending on the connector types. To accommodate fan-out testing, the instrumentation needs to be set up accordingly. An MTP launch cord and a simplex launch cord are necessary. So in this system, you see we have a 24-channel system. We'll have 12 channels dedicated to testing the MPO side of the DUT, and then we'll have a simplex launch cord, which will be dedicated to testing the fan-out side of the DUT. So the referencing process requires 2 steps. First, connect the MPO to the OPM port and reference the MPO channels. Second, connect the simplex launch cord to the OPM port and reference the simplex port. Note that one needs to change the OPM adapter for this step. So previously we had an MPO optical power meter adapter. Now we needed to replace that with a simplex power meter adapter. The measurement process requires the user to manually step through each channel. So first, to test the MPO side of the DUT, connect the launch cord to the MPO connector of the DUT, and then connect channel 1 of the fan-out to the OPM. Continue this process for all channels. So you see here, we've connected the MPO connector of the DUT to the MPO launch cord, right? And then the optical power meter is connected to channel 1, and we're going to measure the insertion loss and return loss at port 1 of the MPO connector. Now we're going to iterate through to channel 2, and then we'll go through and do this for all 12 channels. So you see it's a very manual process. Now to measure the simplex side, to test the simplex connectors of the DUT, connect the simplex launch cord to channel 1 on the fan-out of the DUT, and then connect the MPO connector of this DUT to the OPM. Note, this requires changing the OPM adapter again. Previously, we had a simplex OPM adapter. We had to take off the simplex OPM adapter and put on an MPO OPM adapter. So we connect up our simplex launch cord to channel 1. We're going to measure insertion loss and return loss on the simplex side, channel 1. We're going to iterate through and do this for all channels. So we're going to measure it for channel 2, and then we'll go all the way through, measure all the way through to channel 12. So what we get at the end of this is we'll get insertion loss and return loss for all simplex connectors, and we'll get insertion loss and return loss for all MPO ports, right? So we'll get 24 measurements total. A simpler method is to measure insertion loss and return loss using the unidirectional method. This setup is much simpler and there are less moving parts. The reference setup is very simple. You have your MPO launch cord. Notice you don't have a simplex launch cord for this, even though it's a fan out. So you have your launch cord, you reference your optical power and find the position. And then the measurement setup is you connect up your DUT. So the MPO side of your DUT connects to the launch cord. And then on the back side of the DUT, you're going to connect another receive cord. And this receive cord should be a reciprocal of your DUT. And the purpose of it is to combine the simplex connectors back down into an MPO connector. And in this process, when you referenced with an MPO OPM adapter, and then you also measured with an MPO OPM adapter. For this measurement, you're going to get return loss on all ports on the front side of the DUT and return loss for all ports on the back side of the DUT. And you will get a link loss for all 12 links of this DUT. Now, once you begin assembling and testing MPO assemblies, you will undoubtedly run into various issues. One of the most common issues we see with our customers is that they complain about low return loss on multi-mode MPO cables. MPO connectors that have been used frequently can build up contamination. This contamination can be stuck in the guide pin holes or at the base of guide pins of the reference connector on the launch cord. So on the right here, you see we have 2 MPO connectors that are completely mated. The fibers are all making good physical contact. So this will give you a nice, good return loss result. Now, if we add in some dirt and we try to mate those connectors, you'll see that the dirt prevents the fibers from making proper physical contact. And this will lead to a 14 or 15 dB return loss. Now let's say that dirt finds its way into a guide pin hole and clogs it. So you see the guide pins can't fully insert, which prevents the 2 connectors from properly mating. Again, you get an open, an air gap between the fiber. This will give you a 14 or 15 dB reflection. If MPO measurements are consistently measuring below 20 dB, this might be the cause. Clean the base of the guide pins and guide pin holes of the reference connector. Contact your connector or cable vendor for the best methods to do this. And note, for single mode assemblies, return loss values in the mid 50s to low 60s might also result from poor fiber contact. So an open angled fiber should measure in the 50s or 60s. So if you're not making proper contact with the opposing fiber, you're going to get 50 or 60 dB for your return loss, which points to non-fiber contact. Other issues that might cause low return loss for your MPO connectors, core dips. So core dips can cause a gap between the fiber mating. Large core dips will lead to lower return loss. For the reference cord, it is best to keep core dips low. Optotest suggests core dips of less than 30 nanometers. So here you see we have 2 MPO connectors and they're going to mate. You see they make proper physical contact. The glass contacts each other. However, due to the large core dip, you still have an air gap between the cores. Again, the core is where the light is traveling. So if you have an air gap there, you'll get a Fresnel reflection of roughly 14 or 15 dB. Now, some general rules when testing MPO assemblies. When testing MPO assemblies and there are failures on a connector, it is best to retest the entire connector and not just single ports on the connector. During the retest process, it is possible to get single ports to pass that were previously failing. However, other ports that were passing may now fail. So if ports 1 and 2 of a connector fail and the connector's cleaned and remated, if only ports 1 and 2 are retested, then it is possible other ports may have failed. Possibly ports 7 and 8 have failed, but but that wouldn't be known because they weren't retested. OptoTest suggests anytime an MPO connection is unmated and then remated, the entire connector should be tested, all ports. Mating adapters can get dirty in this process. So dust and debris in mating adapters can dislodge and fall onto the end face of connectors. If the technician is cleaning a connector and it seems like it's still getting dirty after mating, this could be the cause. OptoTest suggests routinely cleaning mating adapters. OPM adapters can also get dirty. So as with mating adapters, if the OPM adapter has dust and debris, it may transfer to the connector. Contact your equipment vendor for best methods to clean OPM adapters. That's about it. Thank you for attending this webinar, and thank you, Shelley and US Connect, for partnering with OptoTest to present this information. We are now open to answer any questions you may have.
Yeah. So Chris, we have a couple questions available to us here, some of them on testing, but I thought I'd start with one on the connector, and a question of being, how many times can the pin change cycle be performed on the Mtpmpo connector? And that's a great question, because physically you can change the Pro connector thousands of times and it will still meet the Focus 5 pin retention 19.6 Newton requirement for the pins. But we've found optically that for multi-mode elite testing, you can really test and use the lead up to 500 cycles of pin change and still get good optical performance with regular cleaning and good cleaning of the end face and the pins. So, Chris?
Okay, I'm just going through some questions here. One question is, can you also go over how to create encircled flux launch condition? That's something that I think after, we have this link here that you can go to after our presentation. That's something we can answer there on how to create the encircled flux launch condition. It's a little complicated to go over that right now. Another question I see here is, I thought bend insensitive would be most preferred as it would withstand the significant bends that might be encountered in a rack-to-rack cabling. Could you clarify on why non-bend insensitive would be preferred in multi-mode? So bend insensitive fiber is good for routing around tight bends. So in typical communication type, applications, so in transmit and receive, that's a good application for bend insensitive cabling. However, for reference cords and equipment cords, OptoTest doesn't believe bend insensitive is the best option. Bend insensitive can affect the launch conditions that you're trying to maintain. So, there's a common requirement for 50 micron OM3 fiber of testing with an encircled flux launch. Bend insensitive has a difficult time of maintaining this launch. So if you have a piece of equipment that has that is encircled flux compliant, if you use bend insensitive fiber as an equipment cord or potentially as a launch cord, you will see that the encircled flux compliance will vary coming out of those cords. So sometimes it'll be compliant and sometimes it won't. Non-bend insensitive fiber is better at maintaining that encircled flux launch coming out of the instrument. We have another. Can we get an overview of specifications, measurement uncertainties for IL and RL for the different methods? That's a good question. It's a long answer. I think, so let's see here. For the two methods that I showed, I can't give exact uncertainties on these, but the two methods that I showed, the single-sided measurement method is probably the most accurate method because you get insertion loss and return loss on each side. So you're going to get, and the values aren't dependent on other connections in your setup. The unidirectional method may have a little bit of additional uncertainty on some of the measurements. So the unidirectional method is measuring insertion loss across the entire assembly. So from, it's going to get ILA and ILB, and those will be a combined measurement. Now, RLA is measured on the front side of the DUT, and RLB is measured on the back side of the DUT. So RLB actually has a little bit of influence due to the insertion loss on the front side of the DUT. So as the light travels through, I actually might be able to go back and look at some of these slides here. But as the insertion loss goes through, so as the insertion loss goes through side A, you're going to lose a little bit of light. And that will affect the measurement for RLB. It'll make RLB look a little bit better. So if insertion loss on side A is 0.25 dB, the return loss on side B will look a little bit better by about 0.5 dB because it's twice the insertion loss of the connector that it went through. So the one-sided method is still the most accurate method. However, a lot of companies are moving towards a unidirectional method because it's a much simpler setup, and they don't feel like they need to know the insertion loss of side A and side B independent of each other. Let's see. Another one, what is the shortest length of the jumper you can test for RL? That depends on the resolution of the system. For the Optotest system, the shortest length that you can measure is 1.5 meters. Another question, are core dips a standard feature in fiber connectors? Is it best, let's see here, stuff's moving around. Are core dips a standard feature in fiber connectors? Is it a best practice from manufacturers or rather a lack of performance? Core dips are actually caused by the polishing process. So the core has a slightly different refractive index than the cladding of the fiber. So when you polish a fiber, a lot of times the core will be removed faster than the cladding. So this is actually just it's a result of the polishing process. So there are polishing processes that reduce core dips. That's why Optotest suggests less than 30 nanometers. That gives you a better return loss performance on your multi-mode connectors. And there are polishing processes that yield less than 30 nanometers pretty reliably. Let's see here. Shelly, are there any questions that you might have? Or I mean, not questions, but any answers that you see for some of these questions?
I tried to answer some questions back only because there was maybe some additional information I was looking for or leaving out. As far as any questions on the Mtpmpo, polarity changing on that and quantity of time of changing on that is, again, thousands of cycles to change polarity key within the Mtpmpo and still be functioning. It's a very easy process, one step with the tool, and provides a very quick ability to go ahead and check and verify your polarity on the Mtpmpo connector. So
let me see here. Another one I have is it possible to get the reliable RL measurements for each of the connectors, MTP and LCs in DUT, which is MTP to 12 LC with a length of 0.35 meters? So it sounds like the DUT is an MTP to 12 LC fan out, and the length is 0.35 meters. So it is possible to get return loss for both of those connectors combined. Because it's a short assembly, the pulse-based method will smear those two reflections together because the resolution of the system is not as small as the DUT. So what you would end up getting with a 0.35 meter DUT would be a combination of the two return losses. So you would get the MTP return loss and also the LC return loss, and those would be combined into one measurement because the length of it is so short. Let's see here.
There was one additional question down towards the bottom here that I saw and I just lost it. It was asking about MPO, IL, and RL standards. And for multi-fiber connectors, you have testing in the GR 1435 specifications for IL and RL requirements within environmental and mechanical test, and also in TIA 568. .3, that is some test plans or some specifications that provide IL and RL test limits.
Another
Chris?
one here.
Oh, sorry, go ahead, Chris.
Oh, no problem. So go for it.
Sorry, I was just going to say there was a question from Greg Bradburn. I just got shifted around a bit, but he had asked this originally. Is the TDR technique useful for multi-mode fiber as well?
What was that?
Is the TDR technique useful for multi-mode fiber as well?
Oh, yes. So the time domain, yes, it's good for multi-mode fiber as well. We presented mostly single mode setups here, but for multi-mode assemblies, the pulse-based method is perfectly fine as well. Another one I have here is, says, can you speak about negative IL values when testing multi-mode assemblies directly after referencing and how to avoid them? So it's a good question. A lot of times that's setup dependent. So when you get negative IL measurements, sometimes that might have to do with an optical power meter adapter that might be damaged. So if you reference with one type of adapter and then you test with another type of adapter, so if you're swapping out adapters during your measurement process, that could affect your insertion loss values and cause them to go negative, which would make it seem like it's a gain, right? Other issues could be fiber handling. So if you've referenced and during your referencing process, you also had maybe a bend or some dirt on a connector while you referenced, and then that dirt or that bend was removed during the measurement process, that would also potentially give negative IL values. Let me see here. Another one, it says, is the term reference cable and launch cable used interchangeably? Yeah, they kind of are. In my presentation, I show equipment cable and launch cable. The purpose for the equipment cable is to protect the equipment, and it's the equipment cable is a large assembly that's kind of difficult to connect and disconnect to the instrument. So you want to leave it attached to the instrument the entire time. And then the launch cord or launch cable is just it's connected to the equipment cable. And then you're going to use the connector on the launch cable or launch cord that is open will be your reference connector. So yes, in effect, they are interchangeable. You're using the reference connector on your launch cord to perform your measurements. And so you could also call it a reference cable. Shelley, you see any others?
No, I did not. No.
So this another, I think this is a follow-up question. It says how to evaluate the combined RL values from both sides of the short cable, which is that 0.35 meter DUT that this person was talking about earlier. It says which value would be considered as passed when we know that this is the combined value. It's a good question. So if you are measuring two reflections that are very close to each other, those two reflections add to each other. Let's assume you have a 50 dB return loss on both sides of that DUT. And those two, if you have a 50 dB return loss on one side and you have a 50 dB return loss on the other side, if you add those two reflections together, right, you don't add 50 dB with 50 dB, that would give you 100 dB. You need to convert those two values back to a linear value and then add them back together again, and then you'll get the resulting actual return loss value. But if you have two return losses that are relatively close to each other, you're getting twice the reflection back, right? So if you have one side is 50, the other side is 50, and if both of those reflections are coming back to the instrument, it's going to be twice the reflection. So it's actually going to be 3 dB larger, which would be 47 dB. It's a little confusing, but we'll probably answer that question a little bit better. We're going to take some of these questions and then answer them on our webpage, and you guys will be able to read the answers to those. Let me see here.
There's one question here. Oh, it just disappeared.
There's a question about 80 micron fiber.
Yeah.
And it says, how is zone B defined? Is it a 10 micron guard band for glue bond and edge chipping, or defined in a different way? That's a good question. We actually got that question before this this webinar, and I'll go find an answer for you, and we'll post it on our website once we actually find that answer. Apologize for not having it. Let's see here, we have another question. If the DUT is made with bend-insensitive multi-mode fiber, how can we test launch cable with maybe receive cable to avoid near zero loss? So this is a common issue with when testing bend-insensitive multi-mode fiber. If you test in the one-sided method, a short bend-insensitive multi-mode fiber assemblies, so let's say maybe 3 to 10 meters long. If you test a one-sided method using standard encircle flux compliant launch, you typically get very good results, overly optimistic results, which which will be close to 0 dB when you're measuring. So there's been some guidance on that testing, and actually the IEC has started talking about how to handle some of that, and then the TIA will actually this week, I think it's either tomorrow or Thursday, we'll be discussing this type of application. So what's suggested is actually using a receive cable on the backside of the bend-insensitive multi-mode assembly. So with bend-insensitive fiber, what happens is the leaky modes or the lossy modes of the fiber don't dissipate very well with length. So on short assemblies, those leaky and lossy modes will continue down the fiber and be coupled to the power meter. So this makes a assembly that should have kind of a normal loss will make it look like it has a very good loss. So what's being suggested is to remove those lossy modes on the back end of the DUT. One would connect up a receive cable, and that receive cable could either be of standard multi-mode fiber, or it could be of bend-insensitive multi-mode fiber that's of the that's the same type of bend-insensitive multi-mode fiber as the DUT is. So little caveat about bend-insensitive multi-mode fiber is that there's a lot of different manufacturers of it, and they all have different structures. So I think there's probably 4 or 5 different brands of bend-insensitive multi-mode fiber out there. They all behave a bit differently when you test them. Some of them will carry those lossy modes much longer in distance. Some of them will dissipate them much quicker. If you're going to be building your DUTs of bend-insensitive fiber and you're going to be qualifying these assemblies, you should communicate with the fiber manufacturer regarding how long they expect the leaky modes to travel down the fiber before they completely dissipate. Let's see here. I think that's about it for questions. So there's another one, sorry, there's a, one asked how to account for the fiber loss in a long assembly in case of unidirectional testing. So the method of unidirectional testing is to test the entire link loss. So when you're testing the entire link loss, you're not worried about each connector by itself, you're worried about the loss across the entire DUT. So in this case, a manufacturer who wants to test using the unidirectional method wouldn't be worried about the long assembly and the fiber loss associated with it. They're just worried about the total loss through the system. Now, when you're testing with the one-sided method, you're looking to isolate the insertion loss to a specific connector, right? So if you have loss through a fiber, if you have a 100 meter or a 1 kilometer DUT and you want to isolate the loss to the connector, you need to subtract out the loss of the fiber. And a lot of times that's just done by finding what the attenuation is of the fiber, and then knowing the length of the DUT, you can subtract out that loss to isolate what the connector loss is. However, with unidirectional testing, you don't necessarily need to, most people who would be doing that would not worry about the loss associated with the fiber. This says, when looking at IL and RL, is there a resolution that the test system has that determines which shortest or smallest component it can measure? Yeah, so most pulse-based systems will give a resolution spec with their system. Another question is there a master plug standard of MTP connector geometry and IL/RL from IEC? Shelley, do you know? I know that that MTP reference connectors have not really been addressed much in the IEC. They tried to keep on addressing it, but there hasn't been much movement with it. Shelley, do you know anything about reference grade MTP connectors and the geometry associated with it?
I do not believe that is set up yet. So I don't have information on the IEC specification. I can look into that and see what's going on with IEC. Yep. There's one question here at the bottom. Well, there's one about debris and dust. I just need to see here where with the potential issue that dirt can cause, what are your thoughts on the importance or necessity of maintaining a clean room environment for MTP or MPO production and testing? And I think that, not everybody can have a clean room environment for testing. If you can, and you're in a lab facility that you can set that up, that would be a great opportunity to do that. But if you're not in a clean room setup, the main thing is still, as we always say, you need to clean. I think that's why we highlighted so much about what happens between the end face of the connectors, that debris can get down into the guide pin holes. It can get onto the end face and prevent your optical performance by being as low loss as you want. So cleaning the end face is always the best thing that you can do if you cannot have that clean room environment. Chris, did you have any thoughts on that?
That's pretty much my feeling as well, is that obviously it's beneficial to have a clean room, but not everybody can do that or have the resources for that. But there's a lot of other other practices you can have, such as cleaning mating adapters, You know, maintaining your reference connectors and cleaning those routinely, inspecting and cleaning. You know, OPM adapters get dirty, adapters to your inspection equipment get dirty. All of those adapters get dirty at some point, so they need to be cleaned and maintained properly to, you know, to keep your DUTs clean.
I think that might be, sorry, I hate to cut this off, especially since we could probably go on and on. We had so many questions come in from the audience. But Chris, if you want to share that last slide for everyone, they'll be able to go to,
yeah, I'm sorry.
No, you're good. You'll be able to go to the link there, maybe in the next couple of days, to check back to these questions and answers that you guys will have posted for everyone. But we will need to wrap things up here. I don't know if you guys had any closing remarks or anything else you wanted to say, but we really appreciate you guys both joining us today. I thought this was very insightful and helpful, and a ton of people are still on, so I hate to cut it short, but we really appreciate you guys joining us.
Thank you.
Thank you. Thank you.
Thanks.
Appreciate it.